All right, class, let's continue our talk about limits and continuity in 1.1. So I just filmed a quick video at first to give you a little bit of a review of functions, and now we're just going to jump straight into business calculus. Okay, so what is the idea of a limit? So it says here, a limit of a function describes the behavior of a function when the variable is near but does not equal to a specified number. So what that simply means is that when talking about a limit, I'll write this down. So when talking about a limit, we are interested what happens to the graph of the function near, in other words, as close as you want. So how close do you want? Well, within a 0.5, within a 0.1, within a 0.001, within a 0.00001 distance is where you can push it as close as you want to a value for x. Okay, so in other words, as you see from this graph, what happens? There's a hole in the graph. There's a hole in the graph when what? When x equals to c, yes? Now the important part is that we are not interested, we can't, right, tell what happens to this graph when x is equal to c. There's a hole in the graph, there's no value. So in other words, f of c is undefined. Why is it undefined? Because there's no value c to plug in, right? There's no y value when x is c. Great, then what can we do? We're going to be looking at the limit of this function. So that's what a limit does. It's allowing us to look at what happens to a function when we're getting near enough to a point, yes, but not exactly at the point. I'm not interested what happens at that point itself. I'm interested in what happens near it. And again, why would I not be interested in what happens to the point? Because for the most part, it's because we can't tell. There's nothing happening when x is equal to c, okay? So that's what the limit is. Now, what do we see from this graph? We see from the graph that as x approaches, I think I spelled that right. Oh, oops, I'm missing approaches, didn't look right. C, and because in mathematics, as I said in my last video, we don't like to write too many words. The symbol for that is this. X approaches c. So x gets closer and closer and closer to c. Okay. What happens to the y values of the graph? Get closer to what? Or approach which value? So as we are zooming into this graph, yes, and we're making the x values from both sides, by the way, get closer and closer and closer to see what happens to the y values. Well, as you see, the y values get pushed closer and closer to this number L. So I'm going to say y gets close to L. Okay, so that's exactly what the limit or the definition of a limit is, right? What happens is what? We're looking at what happens near an x value. Yes, near. Where's my red? Do I have the word near? Yes. but does not equal to, and I'm sure I wrote it, yes, near, right? So what happens near this value, C, yes? And we're looking at the y values, or what happens to the graph there, right? So as x gets close to C, right, looking horizontally for the x values, as x gets close to C, the y values get closer and closer to L, right? And again, I'm looking on the graph, right? So here it is. I'm moving along the graph. I'm getting closer and closer to the C, yes? What happens to the y values, right? The y values are getting pushed up and up and up, yes, with this graph, closer and closer to L. The same thing happens from this side, yes? Getting closer and closer horizontally to this x value. So if you think about all the xy coordinates on this graph, right? So the x's get closer to C, the y's get closer to L. Okay, so that's our limit definition. And this is what we say. We say the limit of f of x as x approaches C is L, right? That's exactly what we said. So instead of writing all this, as x approaches C, the values of y get closer to L, we simply say the limit of f of x as x approaches C is L. And this is what we write. The limit as x approaches C of f of x is equal to L. So again, what does that mean? This means that as x gets close to C, y gets close to L. All right. So I hope this is clear. All right. All right, so let's practice right away. Here's a graph for you, and a bunch of holes in it, even gaps. So let's see what we can say. So I'm going to ask you to find me a few things. What is the limit as x approaches 1 of this function f of x, this blue function? So what you have to do is you have to look on the graph and identify about where does x get close to 1, right? Or where is x of 1, right? And we're looking at what happens to the function as x gets closer and closer to 1. What happens to the y value? Well, sure enough, as we are merging onto 1, yes, with the x values, the y values, looking up and down, get closer and closer to what? Clearly 2, yes? Okay. What is the limit as x approaches 2 of f of x? Okay. So let's find that. I'm going to let you take a minute. Look, you have the notes, by the way, in front of you, the blank notes, hopefully. And you are following along and trying to fill out this yourself. And thinking, again, what else I suggest, and I'm just going to say this because it's one of our first videos, what else I suggest is wherever in the video or in the lecture you find yourself not understanding something, write that down. Yes, we have office hours right away, twice a week. We have Zoom meetings. It's not just about the homework, it's about the notes as well. Where in these notes have you gotten stuck? In the lecture have you gotten stuck? We don't have the luxury of you asking me the questions right away, stopping me right away. So I don't have the luxury of looking at your faces and seeing you confused and not understanding, so I can pause and let you ask or maybe explain again. So we're doing our best, and I'm just trying to give you some pointers. That's why we have, again, the Zoom meetings, so you can ask me these questions. Maybe later on I will explain something else, and your question is not a question anymore because you finally figured it out by page 2 or 3. Once I go over something else, you're like, oh, okay, now the other part makes sense as well. But again, just as I said, try and make yourself some notes so you know to go back to or where to go back to ask me the questions in class. Okay, or in the Zooms, I should say. Sorry, not in class. That's the sad part. All right, so what's the limit as x approaches 2? So again, there's x of 2. I'm looking on the graph, and I'm letting the graph merge closer and closer and closer to the 2 value, yes? So what do the y values get closer and closer to? The y values push up and up both ways to a3. Okay, now again, as I said, I'm not at all interested in the fact that there is no value at x equals to 2. I'm not interested what happens when x equals to 2. All I'm interested is what happens when x is near, yes, near, but does not equal, right, to that specified number of 2. Okay. All right, what is the limit? Moving on as x approaches 3. So same thing, look at the graph. Go a little faster now. I'm getting closer and closer to the value 3, yes. Now what do the y values get closer and closer to? So as I'm looking vertically, yes, to the y values along the y-axis, I see the graph goes pushing down, yes, pushing down towards 1. From down here, it's pushing up towards 1. So from either way, as x gets closer and closer and closer to 3, the y values get closer and closer and closer to the number 1. Now, I again am not interested in the fact that when x in fact equals to 3, yes, exactly 3, the y value is a 2, yes. I'm only interested in what happens as I'm merging on to this point, right, to this x value of 3. Okay, and finally, what is the limit as x approaches 4 of this function? So I want you to look at the graph and see where we're pushing at. So as x gets close to 4, wait a minute, what happens here? Well, I'm getting close to 4, and here I'm getting close to 4. So near the value 4, yes, this is where I'm near the value 4, and a whole bunch of stuff is happening. Coming in from this side, yes, I'm actually merging onto 2. Coming in from this side, I'm actually merging onto 3. The function value is this dot here. That's a whole different story, by the way. So, believe it or not, the answer for this is that it does not exist. And again, we don't want to write too much, right? So instead of writing that, we will just say DNE. So why doesn't the limit exist? The limit doesn't exist because I cannot commit to one number, right? So as I'm getting, we're here, as we're getting closer and closer, we're getting merging onto the same value from both sides, yes? And because we're not merging on, so you can't say the limit is 2 and 3. It's a function, right? So even if we're looking at a limit, we have to commit to one number, right? Just as a function has to commit to one value as we plug in an x, right? So you can't have, oh, it could be 2, it could be 3, maybe 2.5. No, okay? So we have to get one answer. All right. So we will come back to this in just a little bit in this section when we will talk about left-hand limit and right-hand limit. So the left-hand limit exists. The right-hand limit exists. They're different values. So we can be looking at a graph only coming in from one side only, right? One way or the other, right? And a limit, as we will then say, just the limit as x approaches 1 is a double-sided, okay? So meaning from both the left-hand side and from the right-hand side. So from both sides merging on. All right. Now, what if we don't have a graph, but we are given the equation of a function? How can we still determine what the limit is? So here it is. I'm asking you that given the function f of x is 2x plus 3, so just as I said in the first part of this lecture, in the first video, sometimes we're given the equation of the function, sometimes we're given the graph, sometimes we might only just be given a bunch of ordered pairs, by the way. So what if we're given the equation of the function and we want to find the limit. Okay, what are our options? Well, we have a few options. One of them is to make two table of values. What does that mean? So remember, when you're looking at a limit as x approaches 2 of f of x, this is what we have to find, yes? In other words, what values are we looking at? We are not looking at what happens when x equals to 2. We are looking at what happens when x gets close to 2. So what does that mean when x gets close to 2? Well, x could get close to 2. You can write f of x, you can write y, it's up to you. X gets close to 2 means this, 1.9. Yes, that's close to 2. So if you plug in a 1.9 into that function, right, then you don't need to really draw the graph. But let's say we are plugging in 1.9. That seems close enough, right? Just do the math a little bit. You're going to get a 6.8. Can we get even closer to 2? Sure enough, 1.99. Yes, that's closer. Then you will get 6.98. I've already done the math. Can we push it even closer? Sure, 1.999, right? 99999. That will get you a 6.998. Could we have picked a 1? Sure, plug in a 1, you'll get a 5. Yes, but 1 is close to 2, but not as close as we could get with these other values. Now, why isn't this enough? Because remember, just as I said, a limit is really a two-sided limit. You cannot just look at what happens from one side. And let me bring this back. You can't look at just what happens from one side because you might get tricked. Yes, you need to see what happens on the other side of that value. It might be a different number, okay? So this is why I am saying two tables of values. So put in values that are to the right of 2, so a little bit more than 2. Then what are we going to get? We're going to get a 7.2. Can we get, though, closer to 2? Sure. I'm still putting in values larger, yes, than 2, but not so far away. Okay, that's going to be a 7.02. And if you try and push it even closer to 2, right, still those stay on the right-hand side, that's going to be a 7.002. So what do we see? As the x values merge closer and closer and closer towards the number 2, the y values merge closer and closer and closer to what number? You're right, that would be 7. Okay, and the same thing coming in from the right-hand side, in other words, larger values. As we pushing the x's towards 2, the y's get pushed closer and closer towards 7. Yes, so I think we can safely say that the limit as x approaches 2 of f of x is equal to 7. Again, what does this notation mean? That as the x values get close to 2, the y values get close to 7. All right? Okay, now, can we actually draw the graph? Yes, we did that in the first part of the video. So we can try and graph this function. And we did that already. And I know I'm going to have to push up. So okay, so I know I have to push up as far as 7, so that's why I concentrated more in the first quadrant. Okay, so let's see, well, where is the graph of this? The y-axis intercept is a 3, so by the way, if I plug in an x of 0, then I'm going to get a 3. If I plug in a 1 in there, then I'm going to get a 5. If I plug in a 2 in there, I'm going to get a 7. Okay. So We definitely know this function is linear. It's a line. It's not going to have any holes or any gaps or any funny business in it. It's just going to go right through. And by the way, before we even finish this section, we'll talk about continuous functions or continuity of functions. So as you see, what happens to this graph as x merges closer and closer to the 2 value. So as we're approaching closer and closer the 2 value, yes, the y values get closer and closer to 7. We can definitely read this. Okay, now, could we have made this a lot faster, right? Okay, fine, tables are great, graphs are great, but could we have just plugged in the value? I mean, I know we're not looking at what happens exactly when x is 2, but by the way, if I were to plug in a 2 in here, then I'm going to get the number 7, yes? So sure enough, for the most part, that's exactly what we will be able to do. I'll write it one more time. What was our function just to see it? Our function was 2x plus 3, yes? So you could definitely just evaluate it. Just plug in a 2 and you will get a 7. Why is that? Because for the vast majority of functions, really for continuous functions, as we will end this section with, for continuous functions, what happens near a point, is the same thing exactly as what happens at the point itself, right? If it goes through what's near it, that there's no hole, no gaps, then what happens near a point, yes, any point on this graph, is what happens at the point itself, yes? So it goes right through. So we'll just be able to evaluate. As you will see in the next page, these are great tools if we cannot do that, if we cannot simply plug in the value, okay? So, as a matter of fact, we don't have to wait for the next page. Look at this example. I'm giving you another function, and I'm asking you to find the limit as x approaches -3 of this function right here. Okay, so I'm just going to go straight for the end. My goodness. Why can't I just do that? So I'm going to plug it in. X approaches -3. Of that expression, I'm just going to write it down. And let's just plug it in. So -3 squared minus -3 minus 12. I'm just writing it all out just to make sure we're not messing up on our math. So that's a 9 plus 3 minus 12 over 0, which equals to 0 over 0. And I didn't even have to finish, because sure enough, what happens when you divide by 0, no matter what? It doesn't matter what you're plugging in or what you're dividing by 0, even 0 over 0 does not work. So this is undefined. You cannot divide by 0. Division by 0 is undefined. It's not possible. So look at that. We, in fact, didn't get an answer. Why didn't we get an answer? Because sure enough, in this function, -3 is really not part of the domain. Why isn't it part of the domain? Because as soon as you plug in -3, you're going to make that denominator equal to 0. So as a matter of fact, there is a hole in the graph, and you're welcome to put it in your graphing calculators or in Desmos, and really zoom in, because you will need to see that missing tiny pixel in the graph. So there's a hole in the graph at x equals to -3. It's not in the domain. Okay, great. Well, let's make some tables then. All right. So, good thing we're not interested in what f of -3 is. We're interested in the limit, right? So what happens near -3? So what kind of values can I plug in? What about -3.1? What about -3.01? So plug this into your calculator. Put in a negative 3.1 squared minus negative 3.1, and negative 3.1 plus 3, by the way, it won't be 0, right? It will be a negative 0.1. So to save some time, I already did that. So I'm not going to get an undefined because, again, I'm not plugging in negative 3. I'm plugging in negative 3.1, negative 3.01. So these are not going to add up to 0, okay? And then sure enough, we have to go the other way. Negative 2.9 is right to the right of negative 3. It's a little larger than negative 3. That's going to get you a negative 6.9. And that's going to get you a negative 6.99. But again, pause the video, plug in the values for yourself. Don't just believe me, okay? All right, so sure enough, what do I see? I see that as x gets closer to negative 3, the y values get closer to negative 7. Same thing here. As x gets closer to negative 3, the y values also get closer to negative 7, okay? So again, now we know that the limit as x approaches negative 3 of that function is equal to negative 7. Oh, that was a positive 7. Okay, so the point is, you couldn't have gotten a negative 7 out of this one, right? Not in 1 million years I would have thought that 0 over 0 was negative 7, right? But that's what we get when we get closer to the values. And then I will also show you how I actually got those numbers super faster. Also, the graph, again, put it in Desmos. Is a good graphing website. Ooh, negative 7. I should have paid attention. Okay, so let me just do this here. How did I even get those values so quickly? Look at this expression, x squared minus x minus 12 over x plus 3. What could I do with the top? What I could do to the top is I can factor it. That's going to be an x minus 4 times x plus 3 over x plus 3. And then what else could I do? I can definitely reduce the x plus 3's, yes, and then I will get an x minus 4. Okay, don't need to keep the parentheses, but I just left them in there. So this is really what your function is. And again, the only way you can reduce that x plus 3 is if you say that x does not equal to negative 3, because you couldn't divide by 0, right? You can cross out these zeros and end up with x minus 4, right? So you can divide by 0, so as long as you say x is not equal to negative 3, you're safe to go. So this function is really this line with a slope of 1 Oops, I went 1 too low. Negative 4, negative, no, yes. Okay, so what happens is definitely there's a gap. There's a hole in the graph right there at negative 3. But as we're getting closer and closer to negative 3, the y values get closer and closer to negative 7. Okay, now this is definitely a trick that we will be using when we are going to find these limits. Rather than, again, make tables or graphs, we would like to plug it in. So what are we going to do? If I could simplify this rational function, and you guys have discussed and covered rational functions in college algebra, so you've definitely dealt with these type of expressions. You've learned about vertical, horizontal asymptotes, holes in the graph. That's exactly what happens. We get to reduce this common factor, but only if we promise not to put a point when x is equal to negative 3. In other words, exclude it out of the domain, right? So once we cross this out, could I have plugged in a negative 3 in here to find the limit of this reduced function? And pretty much equivalent to this initial function except for this whole? Yes. So plugging in a -3 would have immediately got us the -7. Okay, so I don't like the videos to be too long, so I'm going to stop this one and continue on the next video with the next page.